Welcome to AI Frontiers, where we explore cutting-edge research in artificial intelligence and machine learning. Today's episode focuses on synthesizing recent advances across multiple dimensions of machine learning research. We'll examine how these innovations are reshaping our understanding of artificial intelligence and its applications. This comprehensive overview will highlight key themes, methodologies, syntheses, and scalabilities, and breakthroughs that are defining the current state of the field and pointing toward future directions. Machine learning has witnessed remarkable growth in recent years, evolving from specialized academic research to a transformative force across virtually every industry and scientific discipline. The field encompasses a variety of approaches, including supervised learning, where models learn from labeled examples, unsupervised learning, where patterns are discovered in unlabeled data, reinforcement learning, where agents learn through interaction with environments, and more recently, self-supervised learning approaches that leverage the inherent structure of data to create powerful representations. Our world generates exponentially increasing volumes of data. Machine learning provides essential tools to extract meaningful patterns, make accurate predictions, and automate complex decision-making processes. Current research priorities focus on improving efficiency, ensuring fairness, enhancing robustness, and addressing real-world applicability challenges. These efforts collectively expand the frontiers of what artificial intelligence can achieve through novel approaches and methodologies. The first major research theme emerging across recent papers is decentralized and federated learning. These approaches address the growing need to train models across distributed data sources without centralizing sensitive information, enabling collaborative learning while preserving privacy and reducing communication overhead. Kuttivelil and colleagues introduce Chisme, a suite of protocols designed specifically for fully decentralized deep learning in edge intelligence scenarios. Their work addresses environments characterized by heterogeneous data distributions, episodic connectivity, and limited infrastructure, conditions commonly found in real-world edge computing deployments. The key innovation in their approach is a data similarity heuristic that allows agents to opportunistically infer affinity with each other using existing communication of model updates, enabling more effective collaborative learning. This approach proves particularly critical for edge intelligence applications where privacy constraints prevent data centralization, but collaborative learning remains essential for model performance. Continuing our exploration of decentralized and federated learning, several researchers have developed solutions for real-world implementation challenges. Gokcen and colleagues propose methods for robust federated learning capable of handling noisy and incomplete data, a common issue in practical applications. Their approach implements confidence-weighted filtering to identify reliable data points and employs generative adversarial networks for effective data completion where gaps exist. This addresses a critical challenge in federated learning, where data quality can vary significantly across participating devices or organizations. Taking a different perspective, Pereira and colleagues focus on energy efficiency in federated learning for Internet of Things applications. Their clustering-based approach groups devices with similar data distributions to optimize convergence rates while minimizing energy consumption. This work directly addresses practical concerns for deployment in resource-constrained environments, where power usage represents a significant limitation. Together, these advances make federated learning more viable for real-world implementation across diverse scenarios. The second major research theme revolves around causal learning and attribution mechanisms. These approaches aim to move beyond mere correlation to understand cause and effect relationships in data, enabling more robust and interpretable predictions. Bensina and colleagues present LIDA, a data-driven attribution system implemented at LinkedIn that assigns conversion credits to marketing interactions based on causal relationships. Unlike traditional attribution models that rely on correlative patterns or simple heuristics, LIDA leverages causal inference techniques to determine which marketing touchpoints genuinely influenced user conversions. This enables more accurate assessment of marketing effectiveness and optimization of campaign strategies. The work represents a significant shift from correlation-based to causality-based machine learning applications, addressing a fundamental limitation in many current predictive systems. By incorporating causal reasoning, these models can better explain their predictions and maintain reliability when facing distributional shifts or interventions. The third significant research theme focuses on efficiency and optimization in machine learning systems. As AI applications scale, research increasingly addresses the need to reduce computational resources and energy requirements without sacrificing performance. Pereira and colleagues demonstrate how clustering techniques can optimize energy use in federated learning environments by grouping devices with similar data characteristics. This approach reduces unnecessary communication and computation while maintaining model quality. Similarly, Kuttivelil and colleagues address efficiency challenges in edge computing scenarios with limited infrastructure through their Chisme protocols, which minimize bandwidth requirements while enabling effective collaborative learning. Additional approaches in this domain include model compression techniques, parameter sharing across related tasks, and communication optimization protocols. These efficiency-focused innovations are critical for democratizing access to AI capabilities across diverse hardware environments and reducing the environmental impact of large-scale machine learning deployments, making advanced AI more sustainable and accessible. Synthesizing across these research papers reveals several critical insights about the current state of machine learning. Kuttivelil and colleagues demonstrate that decentralization can enable privacy-preserving machine learning without significant performance sacrifices when appropriate protocols are implemented. The work by Benchina and colleagues provides empirical evidence that causal approaches significantly improve attribution accuracy compared to traditional correlation models, with measurable business impact in marketing applications. Pereira and colleagues show that substantial energy efficiency gains can be achieved through intelligent clustering and collaboration mechanisms in distributed learning environments. Gokcen and colleagues highlight that robust federated learning requires explicitly addressing variations in data quality across participating nodes through filtering and augmentation techniques. Collectively, these findings emphasize that real-world machine learning deployment increasingly demands solutions that can handle heterogeneous, resource-constrained environments while maintaining privacy, efficiency, and performance. These insights point toward a more practical, deployment-focused direction in machine learning research. Across these diverse research papers, several common methodological approaches emerge, highlighting current best practices in advanced machine learning research. Distributed optimization techniques feature prominently, enabling collaborative model training across multiple nodes while minimizing communication overhead. Causal inference methods appear in multiple papers as researchers seek to identify true relationships in complex data rather than superficial correlations. Clustering and similarity metrics serve as foundational tools for grouping related data or devices to improve efficiency and performance. Generative approaches, particularly for data completion and augmentation, address challenges of incomplete or imbalanced datasets. Finally, empirical validation through both controlled simulations and real-world deployments emerges as essential for demonstrating practical utility. These methodological commonalities suggest a maturing field where certain technical approaches have proven their value across multiple application domains and research questions, providing a toolkit for addressing contemporary machine learning challenges. Taking a closer look at selected research, the Chisme protocols introduced by Kuttivelil and colleagues represent a significant advancement in decentralized learning. These protocols enable fully decentralized deep learning in edge intelligence scenarios without requiring central coordination. The core innovation lies in their novel data similarity heuristic, which allows agents to identify potential collaborators based on model update patterns rather than direct data sharing. This approach proves particularly effective in addressing real-world edge computing challenges, including heterogeneous data distributions across devices and episodic connectivity where nodes frequently join or leave the network. The research was selected for discussion due to its innovative approach to enabling collaborative learning without compromising privacy or requiring consistent network connectivity. The protocols demonstrate meaningful performance improvements over baseline approaches while maintaining practical feasibility for deployment in resource-constrained edge environments, representing a significant advancement in edge AI capabilities. Another notable research contribution is the LIDA attribution system developed by Bensina and colleagues and implemented at LinkedIn. This data-driven attribution system assigns conversion credits to marketing interactions based on causal relationships rather than simple correlations or heuristics. The system was selected for discussion because it demonstrates the practical implementation of causal machine learning techniques in a large-scale industry setting with measurable business impact. LIDA represents a significant shift toward more accurate, interpretable marketing attribution that can better inform strategic decisions. The researchers provide empirical evidence showing substantial performance improvements over traditional attribution methods like last touch or time decay models. By incorporating causal reasoning, the system can more accurately identify which marketing touchpoints genuinely influence conversion behavior, allowing for more effective budget allocation and campaign optimization. This work exemplifies how causal machine learning can address practical business challenges while providing more reliable insights than correlation-based approaches. The research on energy-efficient federated learning by Pereira and colleagues addresses a critical challenge in deploying machine learning across Internet of Things environments. Their work focuses specifically on minimizing energy consumption, a primary constraint in IoT deployments, while maintaining model performance. The clustering-based approach they develop groups devices with similar data distributions, allowing for more efficient collaboration patterns that reduce unnecessary computation and communication. This research was selected for discussion because it tackles one of the most pressing sustainability challenges in widespread AI deployment, the growing energy footprint of distributed machine learning systems. The authors demonstrate significant energy savings compared to standard federated learning approaches while maintaining comparable model accuracy. Their work represents an important direction for environmentally responsible AI development, showing how algorithmic innovations can reduce resource requirements without sacrificing performance. As machine learning deployments scale across billions of edge devices, such energy-aware approaches become increasingly essential for sustainable AI. Looking toward the future, several promising research directions emerge from the current work in machine learning. The further integration of causal reasoning into mainstream machine learning applications appears poised to address fundamental limitations in today's systems, particularly regarding interpretability and robustness to distribution shifts. The development of more efficient protocols for decentralized learning at scale will likely continue as privacy concerns and edge computing scenarios become more prevalent. Energy-aware machine learning that explicitly optimizes for both performance and sustainability metrics represents a growing priority as the environmental impact of AI receives increased attention. The field will benefit from standardized benchmarks specifically designed for federated and decentralized learning systems to enable more consistent evaluation across proposed methods. Perhaps most importantly, bridging the gap between theoretical advances and practical implementation challenges remains essential, requiring closer collaboration between researchers and practitioners deploying systems in real-world environments. To better understand the technical innovation in decentralized learning, it's helpful to contrast it with traditional approaches. In conventional machine learning, data is typically centralized in one location for model training, requiring all participants to share their raw data with a central server. The decentralized approach fundamentally changes this paradigm by enabling models to be trained across distributed nodes without requiring a central coordinating server. In this framework, nodes communicate directly with peers, sharing model updates or gradients rather than raw data. This approach faces several technical challenges, including communication efficiency across potentially unreliable networks, handling data heterogeneity where different nodes have different data distributions, and ensuring model convergence despite asynchronous updates. Despite these challenges, decentralized learning offers significant benefits. Enhanced privacy by keeping sensitive data local, reduced bandwidth requirements by sharing only model updates, and resilience to central point failures. These advantages make decentralized learning particularly valuable for privacy-sensitive applications and edge computing scenarios. Causal attribution represents another important technical concept advancing machine learning applications. Traditional attribution models in marketing and other domains typically rely on last-touch heuristics, giving full credit to the final interaction before conversion, or time decay approaches, giving more credit to recent interactions. These methods fail to capture the true impact of different touchpoints in a customer journey. Causal attribution fundamentally changes this approach by estimating the true causal effect of each interaction on the outcome of interest. This approach employs counterfactual reasoning, asking what would happen if a particular interaction didn't occur, to determine genuine impact. Implementing causal attribution requires structural assumptions about how variables influence each other, often represented as causal graphs or models. The resulting insights provide more accurate, actionable information for decision-making by distinguishing between interactions that merely correlate with conversions and those that actually cause them. This distinction proves particularly valuable in complex multi-touch scenarios where traditional attribution methods produce misleading results. This presentation was created through a combination of artificial intelligence and human expertise. The content was synthesized using GPT Anthropic with model Claude 3.7 Sonnet 2025-0219, which analyzed and integrated information from multiple research papers. Text-to-speech synthesis was performed using OpenAI's TTS technology to create the narration you're hearing. The slide visuals were generated using OpenAI's image generation capabilities, designed to complement the spoken content. A human expert review was conducted to ensure accuracy, coherence, and appropriate representation of the technical material. While this presentation has been thoroughly reviewed, some oversights may exist in the synthesis process. All references to original research have been provided to enable further exploration of the topics discussed. This approach demonstrates how AI tools can assist in making complex research more accessible while maintaining technical accuracy through human oversight. To stay updated on cutting-edge AI research, subscribe to our AI Frontiers channel for weekly research syntheses like this one. By joining our community of AI researchers and enthusiasts, you'll gain regular insights into the latest developments across the field. We welcome suggestions for future presentation topics. If there's a specific area of AI research you'd like us to cover, please let us know. For additional resources, including links to the full papers discussed in our presentations, visit AIFrontiers.com. You can also follow us on social media at AI Frontiers for daily updates and discussions about emerging research. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily, Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.